Hello everyone and welcome back. My name is Mr. Kovalt and in this video I'm going to be going over heating and cooling curves. So let's get into this. First, what do the heating and cooling curves show us? Well, there are going to be sloped parts and there are going to be flat parts to this curve, and I'll talk about these curves in just a moment. So the sloped parts of the curve are going to show us where heating and cooling of the substance occurs, whereas the flat part of the graph is going to show us where phase changes occur. And the phase changes are going to be like liquid to gas, gas to liquid, solid to liquid, liquid to solid, freezing, vaporization, things like that. So let's talk about these curves. So here you'll notice that we have a curve here and we have a graph. And so on the x-axis here, we have the heat added if it's a heating curve. So we're looking at a heating curve. So here it's going to be heat added or time over which the heat is added. So the time over which heating occurs. So here I want to point out what the graph is showing. So you'll notice that we have a slope here. And so here we're going to be heating a solid. So we start with a solid because we're heating up the substance. So the heating curve starts with a solid. And so as we add heat, or over time as we're adding heat to the substance, you'll notice that the temperature goes up. That temperature is going up as we add heat. And so once we reach a certain point, it starts to plateau. So here we have a plateau, and so we have this flat range here. And so the important point here to notice is that we haven't stopped adding heat. We're going to continue to add heat. We're continuing to add heat, but even though we're adding heat, the temperature is not going up. We'll talk about why that is in a moment, but at this point, we have melting occurring. So here, the solid starts to melt, and I'm putting energy into the system, but there's no temperature change. So the heat is going in, I'm melting the solid, and I get to a point where I've added enough heat to melt the whole solid that it's completely melted. And so at that point, I just have a liquid, and then the temperature starts to go up again. So I add more and more heat, and now the temperature starts to rise. And so this is where I am heating a liquid. At this point here, I'm heating a solid. Now the solid becomes a liquid, and here I'm heating the liquid. And so as I'm putting more and more heat into the liquid temperature goes up, and I reach a second plateau. And so here, this is where I'm still adding energy again, but now I'm changing the liquid into a gas. I'm vaporizing the liquid. This is where boiling is going to occur. And so I'm going to vaporize that liquid. I'm going to keep adding energy until all of the liquid is vaporized. And then once I get to that point, I only have a gas. So now the gas is going to be absorbing more heat. So as I'm adding more heat, the temperature of the gas starts to increase. And so this is where you can get gaseous vapors that have very, very high temperatures. Okay, so what's happening here? So just to recap a little bit. So again, I'm adding energy to a solid. The solid increases in temperature. So the temperature rises and then it plateaus as the solid melts. Once the solid melts completely into a liquid, now the energy, the heat that's being added goes towards raising the temperature of the liquid. So I'm heating the liquid here, and then it plateaus. I reach a point where the heat is going in and I am vaporizing the liquid into a gas. And then once I add enough heat to vaporize the gas, now the energy I add once I have all gas is going to be put into the gas to raise the temperature indefinitely. So, well, probably not indefinitely, but we'll get into that in a later video. Okay, so this is your heating curve. So if this was water, for example, I would start with ice at a certain low temperature, below zero, and at this temperature here, zero temperature is where the ice would melt. So I'd be heating my ice cube. So let's say I have an ice cube that's negative 20 degrees Celsius. So I would heat the ice cube up until it hit 0 degrees. And then at 0 degrees, melting would start to occur. So the ice cube would start to melt into liquid water. Once all of the ice is melted, all I have was liquid water. And so at 0 degrees, it would start to increase in temperature. So now I will be going up from 0 degrees and I would keep heating the liquid until I got to 100 degrees Celsius. At 100 degrees Celsius, that's when the water would boil and vaporization would start to occur. So now at this point, I'm vaporizing and boiling the water. Once all of the liquid water is vaporized into steam or a liquid water vapor, now I can heat up the water vapor above 100 degrees Celsius. This is why when you have pipes that have water vapor in them or under very high pressures, this allows for the gases to reach higher temperatures above boiling. So this is why if you ever have a pipe burst that has these liquids under very high temperature, you can have gases that are above the boiling points, which could be very dangerous. So, so this is your heating curve. This is your cooling curve, and you'll notice that the cooling curve and the heating curve are mirror images of each other. So in the cooling curve, what's happening is you are decreasing the amount of energy in the system. So you are cooling the substance down. So here you could think of this as the heat added over time. You could think of this as heat released over time. So one of the things you want to keep in mind here is that you're adding heat into the system. So you're adding heat. Heat's going into the system in order to raise temperature and melt and vaporize. Here, energy is coming out. So you're absorbing energy out of the system, and so the system is losing energy. So if this was my ice cube, or I'm sorry, not an ice cube, but if this was liquid water or gaseous vapor, right? So I would start with a vapor here or a gas that at very high temperature. If this was water vapor above 100 degrees, then I would cool the gas down, my water vapor, until I got to 100 degrees. And so in this case, since I'm cooling, the 0 degrees here is not the boiling point, it's going to be the condensation point. So this is where condensation occurs. So the condensation for a cooling curve of a substance, so in this case, say water, that point, that temperature at which cooling occurs is the same temperature at which boiling occurs. So the processes are opposites of each other, but they happen at the same temperatures. So in this case, you're taking energy away, you're cooling the ice, you're cooling the vapor, and then when you get to 100 degrees, let's say, then you'll start to condense, and then you're changing the gas into a liquid. So this is where condensation occurs. Once you've taken out enough of the heat from the water or the water vapor, now you've got liquid water here, and then you can continue to absorb. I'm sorry, not absorb. Take away the heat from the water. You can cool the water down until it gets to 0 degrees. So at 0 degrees in the heating curve, 0 degrees here was the melting going from solid to liquid. At the very same temperature, 0 degrees here, you're going in the opposite direction. So this is where freezing is going to occur. So you're going to go from a liquid to a solid. Once you've taken away enough of the heat from the liquid water and it all becomes ice, now you can decrease the temperature beyond or below 0 degrees by taking away more and more heat. And so both of these are the same process happening in opposite directions. And so the next thing to talk about is what exactly is happening in these flat parts and these inclined parts. So what's happening here and here and here, and what's happening here and here at the molecular level. So that's what I'm going to talk about just in a second. Okay, so the next question we need to ask ourselves is why are some areas sloped and some flat? Well, this gets to the difference in how the energy is being used. So as you are heating up the substance, when we're talking about the issue of whether or not speed is being affected and position, what do I mean by that? So here, remember from kinetic molecular theory that the heat or the temperature of a substance is related to the average kinetic energy of the molecules or atoms in the substance, or the average speed, right? So kinetic energy is related to speed. And so when you're heating something up, right, you are putting energy in. That energy can go in to affect the speed of the molecules, or it can go in to affect the position. And I'll talk about these individually. So here, if the issue is speed, then the energy that's being added is going towards speeding up the molecules. So it's making them go faster. And if the energy is going in to make them faster, then you're going to get a temperature change, because remember, temperature is the measure of how fast the molecules are going. So if the energy is going in to speed up molecules, then the temperature is going to rise. The temperature of the substance is going to go up. And this is going to, again, result in a temperature change. So KMT, kinetic molecular theory. So what happens during the phase changes? So during the heating of the substances, right? So we're talking about here these sloped lines. So here I'm heating the solid. Here I'm heating the liquid. Here I'm heating the gas. When I'm heating these substances in these areas, the temperature is increasing. So in these areas here, the energy that's being added is going towards speeding up the molecules. So what about here at these flat places? What's going on there? I'm still adding heat, but the issue there at the flat places are where the phase changes are occurring. So what's happening? So all of the energy is going towards spreading out the molecules. That is overcoming intermolecular forces. So what's going on here? So here I have a solid. And so when the solid starts to melt, what's going on is the heat that's going in there is no longer necessarily being put in to speed the molecules up. The average speed of the molecules is going to be pretty much constant. It's just that now the molecules are going to start having energy to start to overcome those attractive intermolecular forces that are holding them together. So here in the solid, you're adding more and more heat. And so let's say the molecules are vibrating. So that's really the only movement that they can have in a solid is to vibrate. Well, the more energy you put in, the faster and faster they vibrate, until you get to the point where they vibrate so fast that they start to dislodge from each other. They start to overcome those attractive forces. If this was an ice cube, then the water molecules start to overcome those hydrogen bonding that's holding them together, and then they can start to move past each other. That's what the melting is happening. That's what's happening during melting, right? So melting, you have a liquid, you have going from a solid to a liquid, and when you have liquid water, the molecules now have what is called translational motion or locomotion. They can change place, they can move around past each other. So they're not locked into place, but they're still very close together. So the hydrogen bonding is still active, but they have so much energy that they're starting to break free. And so that's what's happening here. So they're starting to move away from each other, past each other. So they're starting to spread out a little bit more. So they're overcoming those IMFs at that point. So the overall speed of the molecules isn't changing. So you'll notice that the temperature is not increasing. It's not changing here, but it is undergoing a process of melting. And so that's what's going on here. And so this will result in no temperature change. Okay, so at these places here, no temperature change. So at this part here, now the energy is being put into really overcoming those attractive forces, right? So they're going to break free from each other. They're going to move away, and they're going to have lots of space between them. And so they're going to overcome completely those attractive forces and then move away from each other, become a gas. And so that's what's happening here. So the energy that's being put in there is really put into overcoming those attractive forces until everything is a gas. And now you can put in energy to speed up those gaseous molecules or gaseous atoms, and then they can increase their speed and therefore increase temperature. And so that's what's going on at the molecular level. So now we can talk about how the math is going to be related to this, because remember when we talked about in the calorimetry and the specific heat videos that I posted, we talked about how the quantity of heat that's absorbed or released by a substance is equal to MCAT, the mass of the substance multiplied by the specific heat of the substance multiplied by a temperature change, right? So we can, at these parts where you have a temperature change, we can calculate the temperature using that formula, right? So because we have a temperature change. Well, what about here where you don't have a temperature change, yet you're adding heat or you're subtracting heat if it's a cooling curve? Well, how do you calculate the amount of heat that was absorbed here and here if there is no temperature change? Well, that's what I'm going to get into in just a second, so just hold on tight. Okay, so how has our math changed? So let's look at heating, cooling parts of the graph versus phase changes. So as I mentioned before, if you have a temperature change, that means that the energy that's being put in is to speed up the molecules. So you can use the Q equals mass times of the substance times the specific heat of the substance multiplied by the temperature change. So remember, this is the quantity of heat absorbed or released by the substance. So we can use this equation. Why? Because there's a temperature change, and and the reason there's a temperature change and the reason we can use that is because of the specific heat, the units of the specific heat. As I've said in my previous videos, units are important. If you know the units, you can understand why the math is used to get the answers you want. So in this case, we are using our specific heat, and specific heat as energy in joules divided by grams divided by the degrees Celsius. And so in order to get quantity of heat in joules, you need to multiply by a mass in grams, and you need to multiply by the degrees in Celsius in order to get rid of these and only leave you with the energy unit. And so this is why we have delta T in our equation, and this is why we can use temperature changes. So, but we can't use specific heat if there is no temperature change, right? We can't. So therefore, we can't use specific heat for phase changes. We got to use something else. So here for our phase changes, we know delta T is 0. There's no change in temperature, but we also know that the quantity of heat being absorbed or released is not 0. So how do we calculate the amount of heat absorbed or released during a phase change? So what we need to do is get rid of delta T, come up with a new equation that doesn't have delta T in it, and we're going to have to replace specific heat with something else. So we're going to have to replace delta T and specific heat with something else. And so this is where L comes in, which is going to stand for latent heat. So latent heat is the heat in the substance that's used during phase changes, right? So we'll talk a little bit about this later. So we call it latent heat. We're going to use an L for latent heat. So the units here for latent heat is joules per gram. Notice that there's no degrees Celsius. There's no temperature component here. So all you need to know is the mass of the substance and multiply by the mass of the substance, get rid of grams, and then you have joules, which is quantity of heat. So the math is related to the units that you have in the latent heat relationship, whatever the latent heat of that substance is. So this latent heat is the energy required to phase change 1 gram of the substance. Now, you may have seen similar equations. Latent heat, sometimes you'll see heat of vaporization, sometimes you'll see heat of condensation, the heat of freezing, heat of crystallization, things like that. And you'll see also a delta H, right? So the change in enthalpy, that's change in enthalpy of vaporization. So sometimes it's delta H vap, so vaporization, or the opposite would be condensation, right? So going from vaporization would be the latent heat involved in going from a liquid to a gas, or you might have the delta H, the enthalpy of condensation, which is the opposite, going from a gas to a liquid, or you'll have the delta H of freezing versus the delta H of melting. So instead of having L, the latent heat, you could have this, which is basically going to be the same thing. A lot of times, though, the units for delta H of vaporization or the delta H of melting or something like that, instead of grams per, instead of joules per gram, a lot of times you'll see joules per mole as well, or kilojoules per mole. So the units might be a little different here, but they serve the same purpose. So it's pretty much the same equation. Here we're using latent heat in joules per gram. We could use heat of vaporization if that was given to you, right? So if you were given the heat of vaporization in joules per mole, then you could use that in place of L here. So it's the exact same equation that you would use. So for the sloped parts where there's a temperature change, you're going to use Q equals MCAT. For these flat uh, parts of the graph, the where you have this plateau, the flat parts, that's where you're going to use this equation to calculate the heat. So that means that for the sloped parts, you're going to have to be given a specific heats. And so different specific heats go with different phase that you're in. So if you have a solids are going to have different specific heats than liquids. Liquids are going to have different specific heats than gases, right? Even if you're working with the same substance like water, ice has a different specific heat than liquid water versus water vapor, right? So same thing here. If you're using the latent heat, you're going to need to know latent heat of vaporization or the latent heat of condensation or so on, which is I'll talk about in next. So hold on tight. Okay, so the next thing we need to talk about, as I was just mentioning, is that we need to label our specific heats and our latent heats because there are different kinds of each. So when we're talking about heating and cooling, then depending on where we are on this curve, if we're here, if we've got a solid, a liquid, or a gas, then when we're trying to calculate the amount of heat absorbed or released by that substance, then we need to know which specific heat to use. They're going to be different because remember, specific heat is the amount of energy needed to raise the 1 gram of the substance by 1 degree. And so that's going to depend on whether you have a solid, liquid, or gas, because depending on how close those molecules are or how much the intermolecular forces are affecting neighboring molecules and atoms, the specific heat is going to change. So you're going to need specific heat of a solid, liquid, or gas, and you're going to have to use the right one depending on which phase, or I'm sorry, which part of the curve you are on. Okay, so these are always going to be positive values. They're not negative values, so that's important to keep in mind. What about phase changes? As I mentioned, there are going to be different latent energies. And so latent means like the hidden energy that comes from phase changes. So the amount of energy that you need to put into a substance in order to like change it or into from one phase to another, or the energy that you take out of it in order to do the opposite. So you're doing phase changes. So it's that hidden energy. That's why it's called latent energy. And so again, you can have latent fusion, latent energy of fusion, latent energy of vaporization, or I put here also the delta H of fusion or the delta H of vaporization. That's used as well. So remember, these are going to be, as contrary to the specific heat, these can be either negative or positive. So they're going to be a positive value if it's an endothermic process. Remember, endothermic processes is where energy, therm stands for energy or heat. Endothermic means going into. Heat is going into the system or into the substance, whatever your system that you're looking at. So in this case, endothermic, therm, energy, heat going into. If that's going to be positive, so the delta L and the latent heat of fusion and the latent heat of vaporization are going to be positive because you have to put energy into to get fusion to occur. Fusion is just a fancy word for melting. So if you want to melt a substance, you got to put energy into it. If you want to vaporize a substance, you got to put energy into it. So that would be an endothermic process. So the heat of fusion or the latent heat of fusion, the latent heat of vaporization is going to be positive, or it could be negative, right? If it's an exothermic process, meaning energy is going out of, so you're taking energy out of the system. So in this case, you're doing the opposite of fusion, the opposite of vaporization. And so instead of fusion, instead of melting, you're freezing. Instead of vaporizing something, you're condensing it. And so in that case, you're going to have negative values. So this would be freezing and condensation. So down here, I have written that the heat of vaporization is going to be the same value as the heat or the latent heat of condensation, but they're going to be opposite in the sign. So one's going to be negative of the other. So positive heat of vaporization is going to be positive. Same number for the heat of condensation, but it's going to be a negative number. Same thing for the heat of melting or the latent heat of melting. That's going to be a positive value because you're putting energy in, and then that's going to be equal to, but the opposite in sign. This should be a negative sign here. It's going to be opposite because freezing requires energy to be taken out. So these are going to be equal but opposite to each other. So same magnitude, same value, but one's going to be negative, the other one's going to be positive. So what about the putting all this together? But before we put all this together, we need to talk about water and some things that you're going to have to memorize. Okay, so what are some of the things you need to memorize about water? So I have it in this table right here. So for water, you should have these memorized. Now, your teacher may not have you memorize them, but they're things that you should memorize for problems, just so that you have them ready to go for whatever problem that involves water that your professor or teacher might give you. So here are the different specific heats of water: the specific heat of ice, the specific heat of liquid, and the specific heat of steam. And here we have the latent heats of fusion, freezing, vaporization, and condensation. Again, you'll notice that for the latent heat of fusion or freezing are opposites of each other. So it's a positive value because fusion or melting requires the input of energy. It's an endothermic process, so it's positive. Freezing is the opposite process. So basically, it's going to be negative 334 joules per gram. So it's the opposite value from each other. Same thing with vaporization and condensation. They are opposite processes. One is endothermic, the other is exothermic. Same value, different sign. So make sure you memorize those. Now, let's put this together and talk about how you might use this to solve problems. Okay, so now that we have it all put together here, this is our heating curve. So you'll notice here that I've labeled it. So the way you want to use this to approach problems is you need to divide up the curve into its different parts. So I have them labeled part 1, part 2, part 3, part 4, part 5. So for example, if I give you a problem and I say, hey, we're gonna heat up an ice cube. We're gonna raise temperature from negative 18 degrees Celsius to let's say 85 degrees Celsius, right? So let's say that's the problem, and you're asked, well, how much heat was absorbed during the whole process? Well, you have to break up the temperatures according to where the melting point and boiling points are of the substance itself. And so you then calculate each part separately and then add the different quantities of heat together. So in this case, I would get the temperature of negative 18 to 0, calculate that using Q equals MCAT, find that part amount of heat, and then the amount of heat that is needed to melt that ice, right? So I'm going to use then this equation here, and then from 0 degrees to whatever 85 degrees in this range, I calculate the amount of heat used using MCAT again, and then I add those together. And so that's how you want to go about solving the problem.